Welcome to the Section 2.7 pre-class video assignment. Today we're going to look at some applications of some of the second order DEs that we have been solving. So this section is called spring problems, or sometimes it's called mass spring systems. But anyway, basically, we are looking at the situation where we have a mass hanging from a spring, and then it is set into motion by either pulling down on the mass and letting go, or pushing up on the mass and letting go, or we can even pull it down and give it a bit of a bump, give it an initial velocity, and so on. And then the goal is to model the motion of the mass after this. So that is what we're looking at here. Basically, we're going to be working with a function y, which is just the displacement, basically the position of the mass as time goes on. And so that's basically what we're going to try and model here. Ultimately, the physics here is Newton's second law, which basically says that the force acting on the mass is equal to the sum of the forces that we have here. So that's basically our situation. These, again, as I mentioned, are second order and linear DEs, often with a forcing function. And again, in this section, we'll actually see why we call it that. So we have a fairly typical second order DE that we have solved previously by methods like undetermined coefficients and so on. So the first exercise here on my open math is just to try one of those exercises, basically where the forcing function is a trig function. So this is what will be typical in this section. So give that a go. All right, so let's look at our situation here that we are looking to model. Again, so we have a mass hanging from a spring that is set into motion, and we want to consider what are the forces acting on our mass. So there are a few things possible here. Not all are present at all times, but we will look at these in general. The first one, which will be present, is the force due to the spring itself. So the spring itself always has a tendency to pull the mass back to its equilibrium. By something called Hooke's law for springs, the magnitude of this restoring force is proportional to the distance s. So again, if s is distance and F sub spring is the force acting on the spring, then to say that the force is proportional to is to say that there is some number times s here. So our goal here is to find this proportion, this k number here, and this is called the constant of proportionality. It is basically a property of the spring. If the spring is stiff, then the k number is bigger. If the spring is loose, the k number is lower, and so on. In general, when we actually incorporate this into our model, the force here acting on the force due to the spring is considered negative because it is always working in the opposite direction from the mass. If the mass is moving up, the spring is trying to bring it back down again, and vice versa. So the minus sign recognizes this. Initially, though, when we first need to establish the k number here, we would ignore the minus sign. All right, so a little example here, fairly easy one here. If a force of 20 pounds stretches a spring 8 inches past its normal length, what is the spring constant? And so what is the spring constant? So we have to be very careful here with the units. In general, in this course, we're not messing around or being too tricky with the units, but in this section, we kind of are. So want to watch out for the units here. Note that in empirical units, 20 pounds is a force. So we can plug that in directly, right? Our force is 20 pounds. K is what we're trying to find. And then typically then we would use distance in feet. That would be customary here. So 8 inches is 2/3 of a foot. So 20 would be equal to K times 2/3. And from that, we can solve for K and get that K is 30 pounds per foot. So this is the units, the empirical units. Classically, the empirical units for a spring constant is pounds per foot. So that is the spring constant for this particular spring. All right, so other examples you will see in the notes. Well, let's just finish this one off here first. The follow-up question here, how far would a force of 36 pounds stretch the spring? Well, now we have the spring constant. We can solve that fairly easily. 36 is the force. We then have the spring constant is a 30, so we can solve for S. If you solve for S, we get this, or 6/5 of a foot, which is about 14.4 inches. So there's a few examples here on my Open Math to try. They are monkeying around a little bit with the units. So for one of them, maybe empirical. I think the first question is empirical force given in pounds. For the second one, I think the units are empirical, but the force is not given. You are instead given mass in slugs. So you have to come up with force multiplying by acceleration due to gravity for empirical, which is 32. So again, try that one. And then the last one is a metric example. So typically in metric, we would use, again, kilograms, meters, and then acceleration due to gravity would be 9.8. Usually in math, we don't really bother with the 9.81. We usually just go with 9.8. And so on. Now, I think in this one example here, they might monkey around with the units and ask you to do it in centimeters instead of meters. Again, but just pay attention to the units and give those a go. So again, the first one is just I think a normal one like the first one we just did. And then the second one has empirical units, but given with mass, not force. So give that a go. And then the last one, as I mentioned, is metric, and I believe they're giving it to you in centimeters and kilograms. So try that one. All right, so this is our force due to the spring itself. It is a minus Ks. All right, so there is, of course, force due to gravity. If we imagine a spring hanging, then you would have to assume there is some gravity. So this is a little bit of explanation for something that's not actually too complicated in the end, or not too much of a complication for us in the end. But the theory is, initially we would have an unstretched spring. If we then hang our mass on it and just leave it hanging there, we would then consider this to be equilibrium. We have our mass and it is just hanging on our spring, and we now have a length that is the natural length plus the little bit extra because we hung our mass on it. So what happens here is if this is not in motion, it means that the force due to gravity and the force due to the spring are balancing each other out. So if we are in equilibrium, we would have the fact that mg minus ks equals 0. And then the bigger picture for us is that we then set this guy in motion, and this will oscillate back and forth. And that is the motion that we are trying to model. And that is given by this y of t. And y of t is basically based off of equilibrium, not off of the natural length. So if we temporarily ignore friction, which we will till later in the section here, and equate these forces, we have, again, the force of the mass itself. This should be, again, Hooke's law is the spring constant times length. Length here in equilibrium is S plus y. If you plus mg. If you evaluate this, you get, again, a ks and an mg. But notice that mg minus ks are 0, so those cancel out, and we end up with this. So basically, The point of this is that if we work from equilibrium instead of from natural length, then the effect of gravity is already built into the question, and I don't need to address it with its own force term in the model. So that's basically all we are justifying here. I do not need to establish, I mean, basically we have taken care of the effect of gravity by working from equilibrium instead of from the natural length, so we start with equilibrium. All right, so that's the result there. So let's see what else. There can be other forces due to friction, or the fancy word here is due to damping. Experimentally from physics, typically friction damping forces are known to be proportional to the velocity of the body. And of course, again, in this section, the friction is again acting opposite to the motion. So F damp here, force due to damping will be negative, and it is somehow proportional to the velocity here. So C here is some sort of coefficient of friction, and it is positive. The more friction, the bigger the C, and vice versa. We will look often at some examples where the C is in fact 0. So we sometimes ignore friction and therefore just have the C be 0. So the last possible situation that we have here for forces on our system is having some sort of external force acting on our motion. The idea is having some sort of driven motion, having some force driving our mass, not just letting it not just setting it in motion and watching it oscillate. We have something driving our oscillation. So typically, this is an oscillatory force. So it is usually an oscillation, sine, cosine, or some combination thereof. If this force is not oscillatory and just acting in one direction, that is like saying we have an external force where we just keep pulling on the spring, and basically nothing happens. If we just pull it and pull it, it's just going to break at some point, right? So typically the meaningful situation is having an oscillatory force, and you can imagine this as being you have our spring hanging from some support, and then the idea here is that if the support is oscillated while the spring is hanging from it, this would be a driven motion. So we can model this by a so-called, here we have it, the so-called forcing function. This could be our idea of our forcing function. So if we have a forcing function like this, again, it is basically the non-homogeneity in a second order equation, and we've been kind of calling it a forcing function. This function on the right hand side of our second order non-homogeneous DEs, we've been calling it a forcing function, and this is the reason why. That's often what it is representing in an application. All right, so given those forces, the idea is then equating our forces here. We have the following. Again, our mass times acceleration for our mass is going to be equal to, we have a force due to the spring, again, acting opposite to the force of our mass. We have a force due to friction, again, acting in the opposite direction for our mass, and we might have some sort of external force. So typically for convenience, these are then added to the other side, and we can write it in this fashion. And again, what you can see here is that we have a second order linear equation, a second order linear equation. This is what we have been learning how to solve. So that is kind of our situation. So in the rest of the packet, we're going to sort of look at the different cases here. Damped motion would be where there is friction in the system. We're going to start off, and we will look at together now in this video, we will look at the undamped motion case, the simplest case, where we have undamped motion. So basically in undamped motion, that means that we don't have the friction term here. This C is 0 and this goes away. So we end up with either a driven version of undamped motion or an undriven version of undamped motion. This undriven version is known as simple harmonic motion, SHM for short. That is the sort of case we're going to look at together here in the video. This is our simplest case. And again, if we can, in any particular application, if we can identify the mass, if we can identify the spring constant, and again, get some initial conditions, we can solve for the motion of the mass. And in this case, it's actually fairly easy. Again, so here's our first example. A weight of 10 pounds stretches a spring 24 inches. At time t equals 0, the weight is released from a point 12 inches above equilibrium with a upward velocity of 1 foot per second. Determine the equation of motion. All right, so basically, the first thing we need to do is we need to come up with our model, which is I need the spring constant. So again, we can apply Hooke's law. Here, we are given a force. So 10 pounds is appropriate to put in here. In 24 inches, so this is given in inches. This is given in feet per second. Given this mishmash of units, I would go with feet. So 24 inches is 2 feet. So we would get our K number, our spring constant, as K equals 5, right? To solve for K equals 5. So this would be pounds per foot would be the no, again, we don't really need that here, but this would be our spring constant. Then, because I'm given force and not mass, I do need to come up with my mass here. So we know that force is mass times acceleration. So mass times acceleration is 10 pounds for our imperial units. Acceleration due to gravity is 32 feet per second squared. So 32 m equals 10. So m is 5/16. And this is in slugs. So 5/16 slugs is the unit here. Again, not super critical, but I do need to match those up. Right, so I want to be consistent with what we're using here. So at that point, we can write down our model. This is our DE. It is mass times second derivative plus 5 times distance here, or the displacement distance y, and there was no mention anywhere of an external force, so this is homogeneous. But we do have an initial value problem here. We are told the weight was released from a point 12 inches above equilibrium. So 12 inches is, again, in feet, that is 1 foot. So at time t equals 0, we are at 1 foot, and at time t equals 0, the initial velocity is upward of 1 foot per second as well. So these would be this would be our initial value problem. Notice that I have chosen in this section and in your exercises online, that upward direction above the y-axis or above the x-axis or above equilibrium is positive direction. Below equilibrium is the negative direction. I find this is a little more natural for people. A lot of textbooks have that reversed, just in case you're looking in other locations. A lot of places have that reversed, but I'm going to keep it in the more natural mathematical sense. So that is our initial value problem. And again, we can solve this. This is actually pretty easy to solve. It is actually a homogeneous equation. We can come up with a characteristic equation. It has complex roots. Again, complex roots are to be expected here because complex roots gives us a solution with cosine and sine, and that is what we're expecting here. If I have this mass and I set it in motion, it's going to oscillate. So I'm expecting a solution in terms of sine and cosine. So this is our general solution. And again, you can see the work here. We're going to need y prime, and then we can apply our initial conditions, and we can actually come up with this solution as the equation of motion here. This is what's happening. This is our solution function. A quick look-see, I did put this on Desmos. So this is actually the motion as described on Desmos. Again, this is the effect. We have a linear combination of sine and cosine for t here, yes? But notice it really still just looks like something that oscillates. It just looks like something that oscillates, but generally when you have a sine plus or minus a cosine, it just means we have our vertices not at convenient places. So you can kind of see here, and I can't point on, I'm afraid I lose my pointer on Desmos, but we have a peak that is not at 0. There's neither the peak nor the intercept at 0. So this is has sort of been shifted from the usual sine or cosine shape. But what you can see is that this does indeed, when t equals 0, it does indeed start at 1, and it goes up, and you want to be convinced that it's going up at a slope of about 1 at the very beginning. So notice you'd have to kind of believe that that's about a 45-degree angle there at 1 on that line. And again, so the mass starts by going up a little bit. So basically it starts like this. It starts by going up a little bit, and then it starts to oscillate, and actually just oscillates forever in this way. It oscillates forever because there is no friction. We assumed no friction, so there is nothing to stop it from oscillating once it's gotten started. So that's, again, a little artificial, but that was what we assumed in the model. All right, so that is a simple harmonic motion. So there's a little example to try on my open math like that one. Then we want to talk again. There's some general description here of the simple harmonic motion case. Sometimes it is written this way in textbooks, and you can kind of see that if you have this situation and you identify this coefficient in front of y as a perfect square, then you can easily come up with the model as kind of a more formula. But it's fairly easy either way. We also have the idea of the period. The period of the motion is a formula, basically. The period of the motion is how long it takes before it repeats itself. So the period is found by 2 pi over this omega 0 number. And then the frequency is just the reciprocal of the period. The reciprocal of the period basically gives you how many cycles there are per unit of time. You might see these asked for, but they're just a little formula. Probably more importantly for us to look at is the concept of amplitude and phase shift. So we may indeed end up with a simple harmonic motion that is described in terms of a cosine plus or minus a sine term. This is not very convenient. We prefer mathematically to have just sine or just cosine, and it is always possible to rewrite one of these, because it is just a sinusoidal curve. It is always possible to rewrite one of these in terms of just cosine or just sine. So that's what we want to look at here. So it is possible to take one of these and rewrite it in a form so that the curve is equal to either a cosine curve or possibly a sine curve. I generally go with the cosine version myself, but and most of the questions would, if they ask, will be asking for the cosine version. So how do we do that? I think hopefully fairly obviously, we need to come up with the amplitude. If we're replacing the two terms, sine and cosine, with a single term, then we have to have the amplitude, which is the actual wave height, correct. So there is a formula for this. The amplitude is given by, it looks a little like Pythagoras. It is the square root of c1 squared plus c2 squared. So again, here's your c1, here's your c2. c1 squared plus c2 squared square rooted is the amplitude of that sinusoidal curve. I have written up a proof of this fact. This is actually something I think worth going through. It's kind of clever. It's kind of loses some neat ideas. I think it's something you can follow. So this is something I will leave to you to read. But I do have a little problem for you in my open math. So I'm going to have you, it's a scaffolded problem. I'm going to have you work through an example. So this is more a demonstration of the formula than a proof. But I'm going to have you try that on my open math. So we can fairly easily by formula find the amplitude. So once we have the amplitude, we can plug it in if we want to. The other thing we need to come up with to make this equal to the original equation of motion is we need the phase shift. That is, how do we shift sine or cosine over so that it matches up with the cosine plus sine version of it. So we need to compute this phase shift. Again, there is a explanation for that here. The idea here is there are, I should say, there's multiple ways this could be done. This is how I recommend it to be done, however. So as a computational method, I recommend doing the following. That is, you start by computing cosine inverse of this particular quantity here. So do C1 over, so C1 is the value in front of the cosine. If you do cosine inverse of this quantity, you get a result for phi, this the phase shift phi. The problem is that when you get this cosine of phi, you can't tell if you will get basically an angle, and you can't tell whether you want the plus version or the minus version of it. So the trick is to then also compute the sine, and the sine will tell you whether you have to use the positive version or the negative version of phi. All right, so again, here's your formulas, and we will do a little example here. All right, so that's actually a little problem on my open math again to compute the phase shift angle. Again, you're going to compute the phase shift angle using cosine inverse, and then you can use the sine inverse to check it to see whether you want the positive version of the phi or the negative version of the phi. And once you know that, then you have your sine, your phi angle, and then you can plug it in. Again, this is so it is written assuming negative here. So watch out for the sign. If phi is positive, it's minus. If phi is negative, it is plus. So you can plug that in. All right, so that's the idea. All right, so one more little example. This is just an example of this. So let's see. Here we have a mass of 100 grams stretches a spring by 5 centimeters. If the mass is released from a point 20 centimeters below equilibrium with a downward initial velocity of 10 centimeters per second, and if there is no damping, determine the position function y of t at time t. So we are ultimately to give our solution in terms of just cosine and just sine. So that's sort of the exercise here. So let's go through that here. Again, the first thing we need are our parameters. I need to come up with my K number, my spring constant, in a metric case. Mass of 100 grams is 0.1 kilograms. G, acceleration due to gravity, is 9.8. So this is our force. Then the distance in meters is 0.05 meters. 5 centimeters is 0.05 meters. Solving that, we can come up with our K value, 19.6 in newtons per meter. So this is our K value. We can then, well, we have our mass. We don't have to calculate it. So that is given to us. So that determines this differential equation: 0.1 y double prime plus 19.6 y equals 0. And then we have initial conditions here. We have a mass is released from 20 centimeters. It says below there, but I think I have above and down below. I have it as being plus 20 centimeters. So let me fix that real quick. This should be above. And then we have a downward velocity imparted to it of 10 centimeters per second, which is negative 0.1 meters per second. So again, this is a fairly easy second order DE to solve. 196 here, that is 14 squared. So we end up with this general solution. Again, just try the workout here. This is what I get when I solve the initial value problem. So try that out. So let me show you this on Desmos. On Desmos, that was this guy here. So that is this equation here. And then, yes, so this is what this looks like on Desmos. All right, so back to the question here. So the next step is to convert it into just cosine, a function of just cosine. So the work here is I got to find my amplitude. The amplitude is you take the C1 and the C2, right, and basically put those into your formula. I got the amplitude here to be 0.20013. Then this is how I do the phase shift. Again, there are other ways to do it, but I recommend this way. I look at phi as cosine inverse of C1 over the amplitude I just computed, and I get this potential angle. Basically, what this says is that phi here could be plus or minus. Remember, if you do a cosine inverse, the domain of cosine inverse is only from 0 to pi, so it is always positive. I can then check the value of phi. I can apply sine inverse to it and see what we get. And here I get a negative value here. So this is actually not quite the same value, but the point here is that it's negative. So if sine is negative, then I know that I need the phi to be negative. So here is our phi value here, and then I can produce, this would be our cosine version here. I am just plugging it into the formula. Remember that this is a minus. So when I have a phi that is minus, I have a minus double negative here, so it ends up being plus. If I want to make the sine version of this, it is the same thing, except it is just sine, and then inside we have a plus pi over 2. That's the offset between cosine and sine. So this is what we would get. This would be the particular function, again, in the more preferable form, using just cosine or just sine. Typically, you would just need one of these. It asks for both. Real quick then, well, actually, there's one for you to try on my open math there real quick. And then I just wanted to show you really quickly on Desmos. I put all of these in here, and you can see, and this is how I check my work. These can be confusing and can be messy, but if I'm going to check my work, I do the following. Here is the original sinusoidal solution that I got. Then on Desmos, I'm going to graph in, and you could do this on your calculator too. I graph in my solution with just the cosine, and I notice that, yes, that looks like the exact same curve. And then I graph the one with sine, and again, that looks like the exact same curve. So I am confident that those are indeed the correct solutions. And I can check them pretty easily using Desmos. All right, so we're going to leave it there. We will finish up the other cases for simple or mass spring systems in class together. Thank you.